Hello everyone, just a few minutes before we start this webinar on reflecting on the Great Western Electrification Programme. We're aiming for a 6 o'clock prompt start. Everyone here is ready. Just waiting for everyone to join in. There will be an opportunity at the end to ask any questions using the feature in the chat. I make that 6 o'clock according to me. So whilst we just wait for any latecomers to join, my name is Wilson Hill. I am the chair of the Western region of Young Rail Professionals. If you don't know anything about Young Rail Professionals, first things first, we usually tend to shorten it to YRP. It's just easier. It was formed in 2009 to help promote rail as a career path for people to work in. Mostly aimed at sort of the younger generation, but really anyone with less than 10 years experience within the rail industry, or anyone new to the rail industry for that fact. We need to inspire them and develop young people's careers or new people's careers within the rail industry to help them achieve their true potential. Within here, we organise webinars and other networking events such as these, obviously in a COVID environment at the moment, as I'm sure you're well aware over the past 6 months, there have been a lot of online talks and we're not different to that at all. But in an ordinary world, we will have in-person events, which are quite good to meet people from different parts of the industry that you don't really know. We also have sort of trips to different organisations to either help them through charity work. We quite often get involved with the Free Peaks Challenge, having a team raise money for the Railway Children charity, climbing mountains. and get involved in sort of railway preservation as well through our heritage outreach scheme. A good example is we have weekend volunteering trips to North Wales and the Festiniog Railway, helping them to preserve the past to inspire the future. Myself, I'm a train planner at Great Western, which is why this is quite relevant to me. I have done a lot of work which is related to the Great Western Electrification Programme or the engineering blockades. I've been doing that job, was my first and only job really in the rail industry. I joined not long after I finished school in 2016, and now in 2020 I've had spells at Avanti and High Speed 2 working on projects over there as a secondment, but I'm now back at Great Western working on the current timetable, which changes due to needs of the pandemic or engineering work. I'm shortly going to hand over to Matt Jackson and Dr. Dave Hewings, who will be our guest speakers this evening, who have been heavily involved in the Great Western Electrification Programme, and I will let them introduce themselves now.
Good evening all. I'm Matt Jackson, Project Director for Decarbonisation within Network Rail in Western and Wales. I've been on the Great Western Electrification Programme now for 6 years, so know a lot about it, know about a lot of the challenges. So I'm going to talk through that, and I'll just let Dave introduce himself now.
Good afternoon all, I'm Dave Hewings. I'm now the Head of Engineering and Asset Management for Electrification and Plant in Network Rail Wales and Western. I've been involved in electrification of Great Western and particularly its traction power design since 2009. So it's been a long 10-year journey. And I've had several roles through that, but I look forward to going through some of the challenges this evening.
Okay, thanks, Dave. So I'm going to talk to you a bit about what we've achieved to date on electrification, some of the kind of quantities involved in what we've delivered. But then the key thing today is to talk through some of the specific challenges we've had to overcome. And I'll talk through some of the challenges on Severn Tunnel, and then Dave will pick up one of the most challenging bridges that we've had to electrify under. And then we'll hopefully have plenty of time for questions. So we've got a few slides, and hopefully, as I say, if you can get your questions on the chat, we can answer as many of those as possible. Okay. So electrification on the Great Western, it's actually been in the planning since 1965. The drawing there on the left-hand side was the one of the first clearance diagrams that was drawn up. And as you can see with the rolling stock there on the right-hand picture, it's something that has been talked about, developed, and as I say, has been a long time in the making, and it's something that's taken till May 2020 to link the two cities between London and Cardiff, which was one of our key milestones this year. So I've just put up here the passenger services that we've managed to introduce since 2018, and as I say, were finalised in May 2020. This drawing, or this diagram, shall I say, shows the various areas that we've electrified between Maidenhead and Reading, then Reading down to Newbury, Reading to Didcot, and then along the main lines, Didcot to Swindon, and then Swindon down to Bristol Parkway, and then on to Newport and Cardiff. And we did end up going down to Chippenham for a small section as well. So quite, all in all, about 136 miles of electrification, and other areas on that diagram, as I say, were curtailed at various points. But overall, a huge programme. At one point, we had over 300 people in the office working on this scheme. And I can honestly say at weekends, probably, and within blockades, hundreds, if not thousands of contractors. So just talking you through some of the key achievements, that was the the first IET when it got to Swindon in October 2018. Then down at Newbury, we had the 387s were down going between Reading and Newbury as well in late December 2018. And then in Bristol Parkway in late December 18 again, just at Christmas, we got the electrification all the way through to Bristol Parkway, which was one of our key milestones that we hit at the end of 2018. And then the final push to get us to Cardiff in May 2020, that was the first train that ran under electric traction all the way through the Severn Tunnel and through, as I say, Newport and onto Cardiff. So a lot achieved, a lot of hours put in, a lot of blood, sweat and tears, but hugely satisfying and rewarding. Some program statistics that I wanted to share with you, but I think the pictures also do paint a good picture as well. The top left one there was actually a bridge that was demolished to give us the clearance that was required for the wires. The bottom left picture is an example of a parapet extension that we had to do on over 70 bridges as well along the route. And then one of the picture in the middle at the bottom is actually one of the DNO crossings. We had over 30 DNO crossings that we had to review and work with the suppliers, and that was a scaffold tower that had to be erected to protect the infrastructure as the DNO cables were lowered. And then the most striking picture, I think, is the one on the right-hand side, which is actually Wroughton Airfield, which was a huge site that we rented for 5 years, but that actually stopped all of the steel work that was required for the building of the electrification scheme, and it took up such a huge area. The logistics, we employed DHL to manage that site, and they did all of the deliveries out to the various access points along the railway. Just some of the key points that I want to talk through. So over 12,000 foundations installed in the programme, 14,500 masts and booms, which if you don't know, that's the picture in the middle at the top. That's an example of a big 4-track boom there going across the railway. 2030 twin track cantilevers, 9 tunnel interventions, and as I say, we're going to come on to give you a picture of one of the ones that went relatively successfully in Chipping Sodbury, but then I'm going to talk about the challenges in Severn Tunnel. 1,777 kilometres of wiring along the whole route. Interexes, they're the things that tension the wire between each wire run to make sure there is the right tension for the pantograph to run along the wire. 470 switches, which enables us to isolate and move the electricity between the various sections. 109 bridge reconstructions and 86 parapet modifications or extensions. So huge scale of a project, and I'm sure many of you have seen it in the press, both good and bad. But as I say, a very good project to work on, and a lot of experience gained for future decarbonisation schemes. Just wanted to touch that we were quite innovative, and some of this worked well and some of it worked not so well, but we did procure and maintain various train systems that Amy managed. There were various consists varying from the names 1A, 1B, 2A, for example, and these were very specific to the jobs that we asked them to do. So the 1A and 1B was purely a train used for foundations, and then the consists, the 2A, 2Bs there were to do with steelwork and installing SPS. And then the final train, which was actually one of the most successful, was the wiring train, which was all delivered out of Swindon, but really successful. We managed to deliver miles and miles of contact and catenary wire during blockades, which really helped the programme in the end. I've put this picture up because I think this is really a good example of the conductor bar system that we installed in some of the tunnels. This is Chipping Sodbury Tunnel. And then here we had a 6-week blockade where we had to individually drill each of the locations for the steelwork to come down from the soffit of the tunnel. And then we installed the insulators and the conductor bar off the end of them. But as you can see, there are a huge number of engineers involved, and certainly lots of challenges with working in a tunnel environment. But that tunnel is performing very well and is vastly different to Severn Tunnel, where you'll see in a second the environment is very different. At Severn Tunnel, that's the picture from the English side, looking across to Wales. It's 7 kilometres long. It's a brick-lined tunnel with over 3.5 kilometres of it under the Severn estuary. The line speed through there is 75 miles an hour. And we did install the electrification system for up to 90 miles an hour, so it was future-proofed. Approximately 200 to 250 trains use the tunnel every day between passenger services and freight. And there's approximately about there's a train every 10 minutes in each direction. One of the key things about the tunnel is that it's a forced air ventilation system, which made things challenging when working in there. But also in terms of designing the system, because you had to take account of the airflows running through the tunnel as well. A bit of background, it was built here between 1873 and 1886, and it was one of the longest underwater tunnels in the world for more than 100 years. And one of the key facts that is quite interesting, that over 50 million litres of water infiltrates the tunnel every day. And that is removed using a very large pumping system at Sodbury that Network Rail maintains. So the first of the big challenges that we had, which did kind of affect the programme and how we were delivering the scheme, was in 2016 we did install the rigid overhead conductor system within the tunnel in a blockade. And as part of that blockade, we installed the copper wire system. And it was essentially separated by grease. But the challenge that came about not long after was that the copper wire system started to deteriorate, and we couldn't run the risk of that deteriorating in other parts of the system. So between September 16 and December 17, a decision was made that we'd remove the copper wire to limit any further deterioration and impact on the system. And this was mainly down to the environment in the tunnel, which is very unique. You've got various drafts going through there with the forced air system. You've got different types of water penetrating through the brickwork arch, which does give different calcite deposits on the system, and materials do react in different ways. So the long-term solution, after much research and investigation, was to replace the copper contact wire with an aluminium contact wire. So what we had to do, we had to make sure that this new system still met the requirements of the electrification system for the Great Western Railway. It was still compatible with the rolling stock that was going to be running in terms of the IETs and the 387s, which is a long-term ambition. But also one of the key factors was that it was a maintainable system for Network Rail. Because we get limited access within this tunnel, we needed a system that was very robust and allowed the maintenance teams to go in there and inspect it and maintain the system in an easy and affordable manner. So what did we do? We had to do lots of factory acceptance tests. So we brought in universities, we brought in lots of other design houses from around Europe, where we tested the copper wire, the aluminium wire, to make sure it performed in the same manner as the copper contact wires. We had to do lots of tests to make sure the aluminium performed the same under fault conditions, and that's all to do with the risk of a train being trapped or a tripping within the tunnel, to make sure that the aluminium contact wire behaved in the same way. We had to do a lot of metallurgical testing to make sure that the corrosion didn't happen because of the different alloy and aluminium types within the tunnel. But one of the key things that we had to do is that as the pantograph runs over the wire, we had to make sure that the wire wear rates didn't deteriorate at greater than was anticipated for the design of the system. And that's really critical, because the performance of the system is all designed about a maintenance lifetime, and we get funded for replacing wires and things on a cyclical basis. So we had to make sure that the maintenance regime was acceptable for Network Rail, but also for the TOCs, so we weren't demanding more access to maintain the system within there. Okay, so that is a brief run through of Severn Tunnel, some of the challenges, and if I click, I can't see if there's any questions coming up yet, but I'm sure I can have a look coming up to the end. But I'm just going to hand over to Dave now, who's going to talk through one of the challenges on Cardiff Intersection Bridge.
Okay, thank you, Matt. Cardiff Intersection Bridge. So right the way through electrification, from the start of electrification, really in the late 1950s, and it's still a challenge for us now. One of the main issues we face, particularly in the UK, is that our railway structure gauge is generally quite small, smaller than we see in other countries, and so the solutions of electrification in other countries don't always lend themselves to our structures. And the downfall of that is that we often need to do an awful lot of structure moving, track lowering, or bridge lifting in order to get wires through. Now that's one of the main costs of trying to electrify a line, and it can actually be the make or break point of whether it's economic to electrify in the future. So it's been an issue all the way through Great Western Electrification. And looking to the future, if we are to electrify more of the country and look to decarbonise more of the country in terms of its railway system, traction system, then coming up with new innovative ways of dealing with this structure clearance problem has to be what we're about as engineers. Now, the Cardiff Intersection Bridge is a kind of unique challenge, and if you look at that slide there, you can see running from left to right is the Great Western Main Line, the 4-track railway, with just outside Cardiff Central, really. So Cardiff Central is about half a kilometre just down to the left. So as you come out of Cardiff heading towards London, there are lines that head up into the South Wales valleys and head up to Rumney and Cardiff Queen Street, and a ramp takes the line up and over the Great Western Main Line, and then also joins on to the railway that runs down to Cardiff Bay. So there's quite a complex dual bridge crossing of the Great Western Main Line and very limited clearance. Lifting those two railways is obviously a significant challenge, because you can see that would then extend either to changing the ramp back down into Cardiff Central, or having to lift part of the railway up towards Queen Street, and the Queen Street platforms are just off the top of the picture there, so there's a problem. So you might think, well, the obvious solution there may be to lower the Great Western Main Line and do a track lower. Well, this is a perfect storm in terms of clearances, because underneath the railway is the Butte Dock feeder canal. So Butte Dock, one of the major original coal exporting docks of Cardiff, is fed from the River Taff, and there is a feeder canal that takes water from the river and feeds it down into the dock, owned by Associated British Ports, and that sits right underneath that crossing. So to lower the track would mean doing work on the Butte Dock feeder, possibly having to lift the cover off it, the concrete lid that sits on it, and then lower that and replace it, skim it down, replace all the track. And if we just move on, Matt, I think we've got some of the numbers next, have we? Or we've got some more pictures. So this gives you a good example, a good view of the clearance problems that we face there. So this is looking along the Great Western Main Line, and you can see as the railway crosses, we have significant clearance issues running under that bridge. And typically, we would have taken the wire clearance, the catenary clearance, down to about 150 millimeters from a structure like that, which was historically called special reduced clearance, to be used in special conditions, and that's about as low as we're able to go. 150 millimeters and special reduced is another shot of it. Wouldn't get us through here. We just haven't got the clearance between top of the train, pantograph and structure to do that. And so we faced some of the challenges of really looking at whether we need to lift the track, lower the cover of the boot dock feeder, and do a significant track lower under there at significant cost. I think, and that would have been of the order to do the bridge lifting, I think, was between 20 and 40 million pounds, and what we got to was an optimized approach, which was doing that lowering of the track, and even that was 14 million pounds to do the work on the boot dock feeder plus the track. So that's 14 million pounds just to get wires under one bridge. So what we thought of was a completely different approach, never been done before. And it brought together several technologies to try and find a new approach through this, and some innovative engineering from many approaches. Now, if we look at what the real challenge is, and the 150 millimeters, we've got to put that in the context of what is the voltage clearance in air, and 25 kV. The normal breakdown voltage of air is about 15 kV a centimetre. So you could say, well, okay, 30 kV, that would just be 2 centimetres. Why don't you just go down to 2 centimetres? Well, that's the nominal voltage that we see on the wires, 25 kV RMS. The peak of that AC waveform, of course, is root 2, 1.4 times that. So we need something nearer to 40 kV. But you can still see that's way lower than 150 millimeters. So where does the air clearance come from? Well, we need to cover more than just good dry air. We need to cover air in damp, humid conditions, foggy conditions where the breakdown voltage is a bit lower. And more critically, we need to cover more than just the normal voltage that sits on the wire. So the whole system has a breakdown insulation level, which covers transients. Now, there are a few sources of transients. Lightning, which we all understand can put a huge voltage on the system, but also switching. The action of switching circuit breakers puts transients on the system, and we can get an impulse voltage on the system. And our rated impulse voltage level of the system normally is 200 kV. So the clearances that we normally work to and the 150 millimeters all comes back to that BIL of 200 kV. So if we're going to move forward, we need to do something that reduces the maximum voltage of those transient occurrences, that doesn't get in the way of normal 25 kV steady state operation, but clips the peak voltage that can occur. And the best approach to that is to use a surge arrestor. Now, surge arrestors are not new. Surge arrestors have existed on power systems for decades. And basically they have a set of normally resistors inside them, and you connect them between earth and the underlying voltage, and they're non-linear devices. So that once the voltage goes above a fixed operating point, then the device starts to conduct, and it conducts the surge through to ground, and then effectively acts to clip the voltage on the line. So we trialed some new surge arrestors, some new Siemens surge arrestors that we put right next to the bridge. And you can see them in that photograph on the right hand side there. They not only limit the voltage, as we say, and in this case they limit it to 70 kV, significantly lower than the 200 kV, but also they've got a counter system in there, a digital counter system, so that as we try this new approach, and again, it's the first time we've ever done it, we can actually count the number of impulses that those surge arresters see. So through the lifetime of the device, we can see how well this approach is working, and we can go and read the counts remotely, and start to log how many operations of this. And that then sets a trend for us that we can see how we might want to deploy this surge arrestor technology through the rest of the 25 kV network, how it works to cut down over voltages, how often this operates on some of these low clearance bridges, and we have bridges elsewhere that suffer from low clearance, how many times this actually operates, and whether the really low clearance that we've achieved on this bridge actually works. We also did a huge amount of work in looking at what we could do with that clearance, because some of this is due to where the train sits, and where the pantograph sits in relation to the roof of the train. And this has traditionally been a difficult area, because the gauge of the train, of course, is subject to movement of the train sideways, the suspension. So the whole gauge profile, if you're not careful, ends up with a series of tolerances that are put on the suspension system and the pantograph. And if you add all of those up, you tend to get a very worst case number. So part of this work is also about using probabilistic gauging, looking at the likely gauge infringements of the train rather than the worst case, and starting to work to probabilistic limits rather than absolute limits. And we've managed to get the clearances of this bridge down to between 40 and 70 millimeters. It's got 4 tracks. The clearances are different on each of the lines, and the clearance to the bridge from the track is different. But that's a very low distance, as you can appreciate, for 25,000 volts. And one that I guess a lot of us were nervous about when we started. Would this work, or would there just be many flashovers through early operation? Also, if you have a look on the left of that picture, you can see that there's a coating on the underside of the bridge. So what we also did is put into use a new type of insulated coating. It's a you could call it a type of paint, but it's not right to call it paint, because it's a special insulated coating that gives a level of insulation to the bottom of the bridge. So now we have a bridge that has its own insulation layer on the steelwork, which helps us just in case something does bridge that gap of 40 to 70 millimeters between wire and the bridge. And we've also covered the wire with a PTFE contact wire cover to provide additional insulation. So between the coating on the bridge, the additional wire cover to try and help with bird infringements, where birds walk on the wire and their head touches the bridge and so on. And then also that big issue of suppressing the transients on the system and getting rid of those 200 kV transients and bringing them down with the surge arresters. We've got a combination of solutions there that was intended to make the bridge operate at these very low clearances. And that went into service back in December. We energized it last autumn, and went into service with trains running on it and pantographs operating on it in December. Now, leading up to that, as you can imagine, it's a bold thing to do. Would our equipment work with those clearances? And the science of the breakdown of air is not just about a distance and the voltage. So the stress on the air is characterized by the electric field stress, and that's about the voltage and the area. So a lot of it also depends on shape, just in the same way as a mechanical force on the end of a needle will easily pass through something, whereas a much blunter instrument won't, because the stress is lower. It's the same with the electric field. So at high voltages, you'll find a lot of the equipment is specifically designed to have rounded edges to not have pointed features, which at high voltage will put that stress on the air and assist in breakdown. So we took some of our overhead line equipment. What you see there on the left is one of our standard bridge arms, which has a rounded cover on the end. It's a fiberglass device, but we needed to test whether the shape of that at these really low clearances would operate. And you can see that it operated down to 20 millimeters there, and it went through dry and wet testing. This was done at Southampton University, so we managed to recreate the situation of the bridge arm and the contact wire and the cover, and then use the flat plate to recreate the bridge and do high voltage testing to see whether the sort of clearances that we're talking about would be successful. So all of this was put through its testing at Southampton University before we tried it. We got another slide there, Matt, or we? So that really covers the Cardiff intersection bridge. It went into service in December, and compared to other bridges that we have of much higher clearance, since then we haven't had a short circuit fault associated with Cardiff intersection bridge at all, and we've run many Class 800 intercity express trains through it now. Normal service has been running on it for coming up to a year, and we've also run some more challenging stock under it. We've seen charter steam locomotives run under it with very little clearance between the top of the smokestack and the wire, and of course there's a much different stress profile on a smokestack. So we had some challenging mornings of whether that would successfully operate and what would happen with steam and smoke coming out of a steam locomotive. And again, that's been fine. So it really starts to make us think now in Network Rail that the combination of these technologies, the coating, the covers, and also the surge arresters, how we can deploy that for future electrification and really use that technology to reduce the cost of those big civil engineering works that we'd need otherwise. Thanks.
Thank you very much, Matt and Dave. If you've got any questions, please send them in via the function in the software. I have a couple for you, Matt and Dave, if that's all right already.
Yeah, go ahead.
First one from Francesca. How often did the surge arresters operate? What did you find from this, and were they put in place elsewhere?
How often have they operated? Very, very rarely is the answer. There are a few counts in single figures on the surge arresters. We are in the process right now of starting to analyze counts and doing that remote analysis. It's still early days, really. We're still only obviously 8 to 9 months in. As you can appreciate, a large part of that time this year, trains have been running through it without problem. But in terms of access to it, some of that's been restricted by the difficulties that we all face in the last 6 months. So we're going to keep monitoring those counts, but we're talking about a very small number of operations, which could be due to switching rather than issues on the bridge. So I think we're talking about 5 or 6 operations on those. Where they're used elsewhere, we've got one other location on the Great Western Main Line where we fitted it. There's a low clearance bridge out at Mega between Newport and Severn Tunnel Junction, and the same device is used there. It was an innovation that we brought into the program, and you appreciate the program lasted 10 years from start to end, and this was one of the innovations that we've brought in the last 3 or 4 years, plus all the work that you saw there to make it work. So it's really been focused in Wales. The real learning for us now is that this arrangement has been successful so far, and so it's how we would deploy this much more widely on anything else that we're going to electrify.
Yeah, I think, Dave, if I can just add there, it's quite an interesting bridge, that one at Magor, because it's actually one where it's a it's almost 3 spans. It's got a span over the middle, which covers the main lines, and then there's 2 arches on the edges, isn't there? And that's where we didn't want to reconstruct the whole bridge, and it's the arches that create the reduced clearance. So there's just a surge arrestor just on the one side. So it's quite flexible in where they can be located.
Yeah, and I guess that's a, you know, it's a common arrangement in bridges because many lines that in the country that started off as double track lines, and the Great Western line was double track, and the push during the war for coal and steel pushed to the 4-tracking. So you often see that arrangement across the country on 4-track lines, where the 2 original lines sat in a bridge, and then 2 additional arches were created, one each side of it, to take the new 4-track without having to rebuild the original center span. So, and the same with tunnels. Really, you get a common arrangement where either 2 new tunnels or 2 new arches are built, and so having a solution that can go in those end arches, as Matt says, you know, is something that could be useful elsewhere.
I mean, just from a project management and project delivery point of view, I guess, you know, with the current economic climate and the future schemes that we're looking at with electrification, we've got to start utilising this technology, you know, more frequently, because you can't rebuild the bridges because they cost more at the end of the day. It's very simple maths. So we've got to start doing this. You know, if we're looking at electrifying down potentially to other areas like Oxford and other routes like that, we've got to get much more efficient at using these types of technologies.
I'm going to combine 2 questions now from Andrew and Elliot, because one kind of leads into the other. Andrew asks, how will the knowledge gained from this project be shared around the company, given similar challenges will be experienced on the network? And Elliot leads on from that, saying, do you think the lessons learned and engineering challenges faced on this project can be used to drive down costs of future projects such as the Midland Main Line electrification?
Yeah, really good questions. I'll start, Dave, you can finish off if you like. So lessons learned. It's one of the most challenging areas of a project, and it's something that on a scheme like Great Western Electrification, we do lots of lessons learned, lots of good feedback, but it's how we actually use those lessons, as you're alluding to. So there's a national lessons learned database now, which is something that came out of Great Western Electrification. So if the lessons learned is related to construction or engineering or consents or materials management, it goes across the whole spectrum of what you need to deliver a project. So that's something that we've done, and that's something that other schemes can look at. But the best way to get these lessons out to the rest of the business is to talk to people. So myself, it's actually interesting, on Friday, I've got a full-day workshop with Scotland, the Scotland electrification team, where we're talking to them about what we experienced in terms of material procurement, how they installed foundations. One of the big challenges we had, and if you can imagine the geology up in Scotland, quite a challenging environment for them as well up there. So we are talking to other schemes. In terms of the second question about how that's looking to reduce costs in the future, we're doing lots of work at the minute about how our delivery strategy works, because it's all about reducing risk as you go through the development stages of a project for me. So when you start off with a project and it's a kind of outline design, it's how we can look at those costs, which until you completely remove the risk will have quite a big factor of contingency within them. And it's how we'll refine those as we get through detailed design and then through to implementation to reduce and strip out some of those costs. So we are doing lots of work, and a good example of that I'm currently looking at with Dave is how we get a much more robust and simplified foundation that we can install quicker, more efficiently, and is actually can be utilized for a number of different solutions in terms of if it's a mast, a boom, if it's a twin track cantilever, for example. It's almost a foundation for all, so we can get some repetition and some kind of some big factors of speed and etc. to install them. So that's my little bit on that, Dave. I don't know if you think.
Yes, I fully agree with that, and I guess in applying engineering ideas like this and innovation, we've also got to think about how projects operate and risk in project, as Matt says. So a project that's already well advanced, such as Midland Main Line, would already have an approach to structure gauging. Would we change that with some of these? Well, you'd like to think that it can make a step into it, but you've also then got to look at the impact that has on what's already going on, and whether by changing something you actually bring in more cost than you avoid. Should it have been done at the same time? Well, somebody always has to lead with this, and whilst we're saying it worked and it was good, I think it's clear from this presentation that what we did at Cardiff was a big risk. We looked at something that hadn't been done before, but we had to take that bold step at Cardiff to do what we hadn't done before and bring clearances down to a very small level. And if it hadn't worked, I'd be kind of sitting here explaining why it didn't work, and when we had to spend the £14 million to lower the track, and that would have ended up with Cardiff being electrified. So it worked, and now there's that step of, well, now we know it works. How do we roll that out? But at the same time, we've got to think of who does the innovation where, and what does everyone else do at that time. So what we can't do is criticize those who didn't do it at the same time, because that's the nature of innovation, and there will be things going on the Midland Main Line that we didn't do, that will bring us back innovations, things going on in Scotland. The key is that every one of these that we do, we offer up to the rest of the country, and then all try and move forward to bring all of these ideas in the future.
Thank you very much. How many more questions would you like? Because I'm aware it's 6:45.
That's fine.
Shall we call it by
going.
7 o'clock? Does that sound like a good idea?
Yeah, that's fine.
Yeah.
Cool. One from a colleague of mine, James. In the event that the current Great Western Electrification is extended, do you anticipate any other locations providing as big a challenge as the Severn Tunnel or Cardiff Intersection Bridge?
Yes, I do. So there are some. Our biggest structure clearance issue west of Cardiff would have been the famous Brunel arches on the approach to Llansamlet. So between Neath and Swansea, there are 3 arches which were built in Brunel's time, and they're covered with iron ore from the days of Swansea being a metalworking city, and they hold the bank back, and they're severely challenging, probably to the point where even this solution may not have fixed it, because of course you come down to the point where mechanical clearance is foul, and then you have to do something. That's probably the worst case, but the railway west of Cardiff has a much different profile to it. It becomes a more winding railway. It runs north to the edge of the valleys, and then down through Bridgend, and then over Stormy Down to Port Talbot. So you've got a railway there with a lot of bridges, a lot of cuttings, and that's where we would really look at all of these approaches to see if we could cut those down. Some, like the Brunel arches, might not make it, but that's the most challenging one to the west.
Yeah, I think for me, if I come back further east, I think one of the challenges potentially, if we do ever electrify up to Oxford from Didcot, is that it's actually a fairly constrained footprint that we've got to try and build of electrification on, and there's lots of other schemes within that corridor which may take place at the same time. So one of the big challenges is integration for us, which is something that we do as project management kind of team. But you wouldn't actually, probably one of the biggest risks on a scheme like the Oxford corridor is actually consent and third parties, and that's something that we're already beginning to look at and see how we can influence external parties, because the kind of corridor, as I've said, electrification would have an impact on there with big booms, big portals. There's some areas of they're not AONBs, but they're certainly conservation areas, for example. There's lots of marshland and wetland around there, just south of Oxford. So a lot of mature listed trees with tree protection orders on. So it's a lot of consents as well. It's not just building this the system, it's the interface it has with the environment around it as well. So consent is one of the big challenges for me. But technically on that route, there's a particular location called Appleford, where we've got a station right next to a listed bridge. And again, we're looking at the optioneering there in terms of clearances, so we can hopefully not have to rebuild a station to maintain the bridge or vice versa. There's lots of optioneering to do around that particular location, which will be a technical challenge as well.
A question from Edmund kind of links into one Andrew who's asked as well, but is there a case for discontinuous electrification for future stages of the Great Western Electrification Programme before the full extent of electrification proposed by the TDSC, which I think is the decarbonisation, unless you know more than I do?
TDNS, the Traction Decarbonisation Network Strategy. So I've been part of that for 2 years, and we're looking at decarbonisation plan for the whole of the Wales and Western region network. Discontinuous electrification's been a discussion point for I guess the last 4 or 5 years. I think where this is going, and this is still a moving position really, we are now starting to see that the future will be far more about a combination of independently powered traction plus electrification rather than the either or that we've seen in the past. I firmly believe that we won't wire the full extent of anything in the future, that we will start to integrate more with particularly battery powered trains, and the combination of charging on wires and running off wires with batteries will be what we see. That will, you could call that discontinuous. Discontinuous is more closely associated at the moment with not wiring a particular feature, a station, a tunnel, a bridge. And there we have to look that if you just leave a small gap like that, you still have to get power past it. The very nature of traction power means that, yes, the wires take power to the train, but they're also there to move power down the railway. And if you don't wire it, you have to then cable through that feature. And one of the things we know is that cabling can be more difficult than the wiring. So I would say for the small discontinuous bridges, stations, our approach in the future would be to try and do more with bare conductors, use the low clearances, push it to as far as we can in terms of that technology, because the more that we keep it up in the air and use bare conductors, the lower the cost than if we start going to huge amounts of low level 25 kV cabling. But in the wider sense, I think we will see a combination of branch lines and main lines that are wired and not wired. And personally, there are other technologies that in the substations we've deployed a substation communications technology, which is a world standard called IEC 61850, which vastly opens up the intelligence of our traction system. And I foresee a time where train and track are talking to each other in energy, and we have the ability to raise and lower pantographs automatically with that technology integrated. And then you could even see a world where we would just wire plain lines and we wouldn't wire crossovers, and you'd be able to move from one line to the other using battery technology. Now, if you could do that, then you remove an awful lot of very small wire runs through complicated junctions, and that represents a large amount of cost for very little single track kilometre volume in terms of your wiring. It vastly simplifies the overhead line system. It makes it a bit more reliable because those junction areas are difficult. They're difficult to maintain. They're difficult to get at. They're difficult to wire in the first place. A lot of masts, a lot of anchors. So I think if we look over the hill in terms of where technology going, that's what discontinuous will probably become.
Cool. Thank you. Let's go for, well, two more. One I think you've covered quite well, but I might want to put a final note on it from Michael. Do these new technologies make track slowing, lowering and bridge raising unnecessary from a cost perspective?
Yes, I mean, they reduce them. As I say, the ultimate problem is where you haven't got mechanical clearance. If you can't actually fit the pantograph and the train under the bridge, you're stuck. There's no technology that's going to get you through that. So there will always be a place for a level of track lowering and slewing and bridge lifting. But track lowering comes with its own problems, drainage being one of them. And there's no doubt that the future will be about squeezing down the clearances to do less of it. So it won't go all together, but our aim will be to do a lot less of it on any electrification scheme.
Yeah, I can't add much more to that. I think at the start of Great Western Electrification, looking back, we undertook lots of track lowering schemes, and you know, they take up lots of train movements, lots of planning, generally need lots of blockades, which isn't great for passengers and freight. So we've got to think about that overall impact.
Not great for people like me who have to then deal with all the timetables.
Exactly.
When you close the railway. Work piles up. Finally, one more question from Andrew, which is more towards the London end of the route. How, if any, if there were any problems with electromagnetic compatibility with older stock, so mainly sort of the Heathrow Express 332s or the Connect 360s?
I'll pick that up. Okay, so electromagnetic compatibility. So the introduction of new trains, I think, has been an issue. I specialised in an EMC of new trains back in the early 90s, and it was a time when we moved from phase angle control drives and the historic approach of low order harmonics on the AC to the use of switching drives of GTO thyristor technology, the sort of technology that's in 332s. And there were some train safety cases and EMC safety cases in those days. And I was involved in the technical development of some of them that became really, really complicated, and a real challenge for the industry of not just whether it was compatible, but how you prove it's compatible and how you go through all of the failure modes to demonstrate it's compatible. In a switching converter, that's obviously a big challenge that the industry hadn't faced before. And there are a notable number of rolling stock types that were probably put through the mill far more than what followed. 332 is one of them. The Class 92 freight loco stands out as one of them. Eurostar and the later versions of the networker EMU, the Class 365 and Class 465. Very detailed safety cases, which led on to later builds of traction, such as DeZero and Electrostar, becoming a lot simpler to do and following established patterns of what emissions were acceptable and what emissions weren't acceptable. Electrification hasn't really changed that very much because, of course, the 0 to 12 electrification was already there. And whilst there are EMC and EMF issues associated with electrification, the far bigger issue with EMC still today is that compatibility between the switching harmonics and line side signaling and telecommunications. Now, over the past 5 or 6 years on the Great Western Main Line, we've seen new challenges in that, back to traction converters, back to having to do a lot of work of looking at high frequency harmonics and telecommunications interference, all down to the fact that what we're seeing now, the move from GTOs to insulated gate bipolar transistors, the switching frequency of converters has gone up, and so we're seeing occurrences now not in the sub 1 kilohertz, but up in the 5 kilohertz, 6 kilohertz, 7 kilohertz, 10 kilohertz region, where it becomes much more difficult to analyze. But primarily, this is still an issue about how we manage train introduction and how we manage analysis of those emissions, rather than something really embedded in electrification. It will carry on being a challenge, but we've got to apply some of those simple principles post that first set of traction classes back in the 90s, where we managed to get on top of this issue, and we had a lot of successful train introductions with no problem at all. Does that answer it?
Answers it for me. If I hear anything from Andrew, I will let you know. But I thought that was fairly comprehensive, Dave, so thank you very much. Thank you also to Matt, and well, generally thank you to Matt and Dave for giving up their time to give this wonderful and very detailed and interesting presentation. Especially from my point of view, we just see these as problems that we have to work around. We don't actually understand or get told the engineering complexities behind them, and so on and so forth. We're always, oh, can't you just knock the bridge down? But these guys come up with very ingenious solutions to solve a problem that nobody else has thought of. So thank you very much for coming to speak to us.
Oh, not at all. A pleasure.
I hope it was okay.
Yeah, it was fantastic. Thank you very much. And
Thanks.
to anyone that's tuned in this evening, the Western region of Young Rail Professionals is relatively new. It's just restarted after an absence, and I am looking forward to people who would like to be more involved. So if you would like to be more involved, please ensure that you sign up via our website and just drop me an email or a message. My email address is widely available on the website. And if you would like to join the committee, just drop me a line and let me know. Thank you again, Matt and Dave, and everyone else for joining.
Thanks very much.
Hope you all have a good evening.
Okay, thank you.